We're going to continue with kinetics today, fitting into big idea 4. Yesterday we left off with rate laws. I'm going to go back and review that concept with you. Remember, we were talking about rate laws, and we said that if you have a rate law such as this, the order with respect to A is what? 3. The order with respect to B is? 2. Overall order is? 5. And you can get units of K as molarity. 1 minus overall order would be? How about 1 minus 5 is? -4. And then time to the -1. So that would be your units of K, and that is very commonly asked. So you really want to make sure you're comfortable with units of K. We see that very often. We also had worked on determining rate laws from experimental data, and that is shown here. We had walked through this, and we'll do one from scratch to make sure that you've got it. Again, this is something you want to be able to do without a calculator. So what we're looking here is at a synthesis reaction. 3 experiments were run. Initial concentrations of nitrogen monoxide and chlorine gas were given. And then we're looking at the initial rate of formation of the product in molar per second, because that's a rate as opposed to a concentration where you just have a unit of molarity. You'll be asked to determine the rate law from the data provided. This will not be given. You'll need to figure out your rate law, determine the N and the M. This was M. We must have determined what it was yesterday and stuck it in. Okay. In terms of this approach, as we talked about the other day, you want to hold one concentration constant and look at the effect of altering the other concentration on the rate. What you are investigating has to change in concentration. If you divide those two concentrations and you have 1, you're not looking at the effect of a change. Be careful there. I've seen kids do that. So you can hold it constant in experiments 1 and 2. You're holding nitrogen monoxide concentration constant. You can see here that this is doubling. When this doubles, you can see the rate doubles as well. So you've got the concentration of chlorine in the second experiment over the first raised to the M, because chlorine is the second reactant. The rate of the second over the rate of the first. Plug in those values. Without a calculator, you can do this. 2 to the M is equal to 2. M is equal to 1. That means the reaction is first order with respect to chlorine. Whatever you do to the concentration of chlorine is exactly what you do to the rate. If you triple the concentration, you triple the rate. If you quadruple the concentration, you quadruple the rate. If you half the concentration, the rate is half as fast, or more commonly stated, the rate decreases by a factor of 2, the reciprocal of what you got. Now we want to look at the effect of nitrogen monoxide on the rate. We're going to hold chlorine constant, and you can see it constant in experiments 1 and 3. It's not changing. So we're going to divide these 2 to the N. We're going to divide these 2, and that's shown below, where you have nitrogen monoxide in the third experiment over the first to the N, because nitrogen monoxide is the first reactant. The rate of the third over the rate of the first. You have 2 to the N is equal to 4. N is 2. The reaction's second order with respect to nitrogen monoxide. Now, from what they showed you initially, again, this would not be given. You rewrite this. You know your N is 2. So you've got an exponent of 2 here. Your M is 1. You've got an exponent of 1. Your overall order here is 3. So what would the units of K be in this example?
K -2, time -1.
Yeah, it's molarity, 1 minus overall order, so it's molarity to the -2, as you said, time to the -1. All right? Now, you can calculate K, and that's what they're asking for here, and let's take a look at that, and we're going to do a lot of analysis here to make sure you understand the rate law. Again, rate law really exemplifies the effect of concentration on the rate.
What if you get like a fraction like 2/5 as your N or M? How would you say like increases or decreases by a factor?
That one would be very, very tricky. You basically would do the math on it. I don't think you would be asked for that. If you got a rate law with a fraction in it, you would write the rate law with the fraction. You could still look at K units, but in regard to interpreting it, if you got a fraction, I think the only fraction you would get would be like a half. So I don't think it would be nearly that complicated. And if you got something like that, you're not looking at a multiple choice fraction in regard to the interpretation, where you could plug values in and raise them to exponents that were fractions. But I think you're making it harder than what I think they'll do to you. I've seen a few rate laws with fractions, but typically they're halves. And I'll pull some old problems and we'll take a look. Okay, so you can calculate K. So the rate law that we got was rate is equal to K nitrogen monoxide squared times the concentration of chlorine. If we wanted to calculate K, we would solve for K. So K is equal to the rate over nitrogen monoxide squared times chlorine gas. And now I can just go back to my data table and I can pick any line I want unless they specify for a particular experiment. If they don't specify for a particular experiment, I typically just look at experiment 1 because I have the least chance of eye flippage. So if I look at that first row, I can plug those values in where rate is 2.27 times 10 to the -5th molar per second. Concentration of nitrogen monoxide is 0.0125 molar squared. And concentration of chlorine gas is 0.0255 molar. And again, you can see your units of K that you mentioned earlier, m to the -2, seconds to the -1, because you'd have m over m, cubed. So 1 minus 3, again, -2, and this seconds is the denominator. So seconds to the -1. And then this would be calculator-based math. If you got something that wasn't calculator-based math, it would be very, very easy. So what we've got here is 2.27 EE -5 divided by 0.0125 squared times 0.0255 close equals. And you have 5.70. And my unit's sort of swimming in the back there. All right, so you can calculate K, no problem. We want to be able to interpret it, and then we're going to walk through several examples so you can see exactly how to work this. right, so I've just given you a whole bunch of scenarios here, and you've got this in your notes. I'm going to show you mathematically because I think it'll be easier. We want to look at the effect on the initial rate that's caused when you double the concentration of one reactant while the other is held constant for 0, first, second, and third order. There are many, many examples you can use. So if you have any generic rate equation, let's say you have rate is equal to, let's say your equation is y, no, I'm sorry, x yields y plus 2z, just for simplicity. If you have 0 order, as it states in number 1, the rate is just equal to k. So concentration's not in the rate law. It doesn't matter what you do to the concentration. There's no effect on the rate. If you have first order, where rate is equal to k times the concentration of x, if you double the concentration of x, then the rate doubles. So whenever you have first order, whatever you do to the concentration is what you do to the rate. If you have second order and you have rate is equal to k, concentration of x squared, if you double x, what happens to the rate? It quadruples, right? So the rate quadruples or increases by a factor of 4. And in the last situation, let's say that it's third order with respect to x. If x is 2, so you double the concentration, 2 to the third is, oops, it's of course 8. That's all right, we'll work on it. So the rate increases by a factor of 8. Now, what if, go ahead.
That's what I was saying, because like if it was to be x to the 1/5 and then you had 2 inside of it, then
you'd have a mess, and that would be too tough. But you raise a good point. So if you had a half order, okay, if they did it to you, they're going to give you something easy. They might say, okay, you quadruple the concentration, what happens to the rate? It doubles. Or they give you, okay, you have the concentration upped by a factor of 16, what happens to the rate? Exactly. But that's really, I think you're smart in thinking, okay, what kind of trick could they throw at me and I'm going to be ready for, which is, for AP Chem, is super smart and insightful. But you may be making it harder than it probably needs to be. We used to do a lab where we did get, from experimental data, we got fractional orders. There are ways to do it. You can do, keep in mind if you didn't know that something to the half power was this, you could do it logarithmically. You know how to do that? Where you could swing it. If you had, for example, let's say 3 to the 2/5, and you're trying to figure this out, you can do it on a log basis. You can do 2/5 log of 3 is equal to the log of x. And then you can work it out. But it's not going to be that hard. Yeah, it starts to get ridiculous.
Can we just do 3 to the power of 2 divided by 3 to the power of same thing? I'm not sure. That's one that's.
Let's see. So if you had the log of 3 and you multiplied that by 0.4 and then you did anti-log, you'd get, what do you want to do? What do you want to do?
I wanted to say 3 squared, I'll do divided by 3 to the power of 5. Yeah, that's not right.
It's not right, so then the answer is no.
These calculators, can't you enter in 3 to the power of 2 fifths?
Yes. You could do 3, arrow up, open parentheses, 2 divided by 5, close, and get the same thing. Yep. But if you had this situation where, let's say you had 8 and you're trying to figure this out and you're at this, that's when you're going to need the log swing around. You'll need n log of 8 is equal to log of 3, and you'd need a swing around. So that's why I mention it. But absolutely, if they give you this, you can get that. But if they do this, then you're going to need n log of 8 is equal to log of 3, and then you would do that. But you're making it harder than it is. It's not going to be that hard. I mean, AP Chem is ridiculously hard, but this is getting even harder than they're going to make it. All right. Did want to mention one more thing. Now, if, for example, this whole thing was just doubling up the concentration, but if, for example, you half the concentration, what is 1/2 to the 3rd power? 1/8, right? So here, what you're looking at is you typically wouldn't say the rate is 1/8 what it was. You would say the rate decreases by a factor of 8, the reciprocal, all right? So if you half the concentration here to the 3rd power is 1/8, and you would say the rate decreases by a factor of 8, which is the reciprocal. All right, so we have another big problem here, and the answer is given, but I want to see if we can work through this. So they give you an equation. They have mercury 2 chloride reacting with oxalate ion to generate chloride ion, carbon dioxide, and mercury 1 chloride. And this is a redox reaction. Ooh, this looks like fun. It says determine the order of the reaction with respect to each reactant and overall, write the rate law, calculate the value of K and indicate units. What would be the initial rate of the reaction if the concentration of mercury 2 chloride is 0.020 molar and oxalate ion is 0.22 molar? Calculate the initial rate of disappearance of mercury 2 chloride in experiment 1. So there is a lot going on here. This would be more of a part 2, although you probably could get the rate law without the calculator. So where do we start? What do we do? Help.
You take the 2 experiments and determine the order of the
Right, you want to figure the order of each the order with respect to each reactant, and in order to do that, what must we do? We must hold. Go ahead, Ethan.
First reactant constant.
We're going to hold one reactant constant and look at the effect of the other. So in looking at our data here, we can see, and again, there's no good place to start. It's whatever you see initially. I see constant concentration here, and this one is doubling. So I'm thinking of starting with experiments 1 and 2. I can see that this doubles, and what's the effect on the rate? It quadruples. So what I'm looking at here, and again, without a calculator, great. 2 to the m is 4, m is 2, second order with respect to oxalate ion. In terms of writing this out initially, because many of you are new to this, what you're looking for, what I typically do is I say to myself, hold the mercury 2 chloride constant. I'm looking at the effect of oxalate ion on the rate, and I'll write 1 and 2, so I know I'm using experiments 1 and 2. And that's enough to get me going. I'm looking at the change in concentration of oxalate ion in the second and first experiments. I'm going to raise this to the M because the oxalate ion is the second reactant. And then I'm going to do the rate of the second over the rate of the first. I have 2 to the m is equal to 4. And again, if you have the same exponent there, 72 over 18 is 4. Make it easy for yourself without that calculator. M is equal to 2. That's going to be second order with respect to oxalate ion. Okay? That's the first part. Now, for many of you, this should look familiar. I can't emphasize enough the importance of working through rate law problems over the weekend such that you are an expert in writing rate laws come Monday. All right, now we need to go for the next piece of the puzzle. What am I holding constant? What's going to change? You're going to hold this constant. You're going to look at the effect of the change on the rate. And again, I typically put the larger concentration in the numerator. It makes the math easier. There's always one kid who wants to do everything in fractions. That's fine. Don't make a mistake. So what we've got here is we're going to hold oxalate ion constant. We're going to look at the effect of mercury 2 chloride concentration on the rate using experiments 2 and 3. Now, in terms of your analysis, what you need to show me, you don't need to write this whole blah blah constant. I just wrote it in for you because I thought it might be helpful. But I certainly do want at least this piece right here, so I know what experiments you're going after. Otherwise, it is very challenging to grade, and if you make a mistake, I'm not going to know where it is. 0.105 molar over 0.052 molar. Again, I put the larger quantity in the numerator raised to the n because mercury 2 chloride is the first reactant. And that's going to be, just be consistent here, experiment 2 over experiment 3 in regard to rate. 7.2 times 10 to the negative 5 molar per minute over 3.6 times 10 to the negative 5 molar per minute. and that's going to be 2 to the n is equal to 2, and n is equal to 1. So first order with respect to mercury 2 chloride. Now that I have all of that, I can write my rate law. I've got rate is equal to K. First reactant is mercury 2 chloride. That's to the first power. Second reactant is oxalate ion, and that's to the second power. So that's my rate law. Here's the answer to A. And again, all of that could have been done without a calculator. What's the overall order? 3. What's the units of K? Molarity to the -2, minutes to the -1, because you've got minutes built into that rate. Part B asks for the value of K. Again, they don't specify which experiment. Pick the first one, because it'll be easier for you. K is equal to rate over mercury 2 chloride, oxalate ion, squared. Don't forget to square. That's the most common error that kids will make. I'm using the first line of experiments. If you can't remember how to do units of K, you can get them from your problem here. But it's nice to be able to know how to do it. It's a good shortcut. It also makes sure you set things up properly. And that's going to be 7.6 times 10 to the -3 molar to the -2 minutes to the -1. And again, not challenging. All right. The next question says, what would be the initial rate of the reaction if the concentration of mercury 2 chloride is 0.02 molar and the concentration of oxalate ion is 0.22 molar? Basically, what they're asking for in C is they want the rate of the fourth experiment. How would you go about getting the rate of the fourth experiment? Go ahead, Chris. It's as easy as you think. You got it. You worked so hard to get a rate law, plug it all in. Here's your rate law. Use those K's and concentrations. You have rate is equal to, here's the K, 7.6 times 10 to the -3rd, molar to the -2, minutes to the -1. This concentration is 0.020 molar. This concentration is 0.22 molar. Don't forget to square it, otherwise your units won't cancel, so you should catch it. And what you've got is 7.6 EE -3 times 0.02 times 0.22 squared, and that's going to be equal to 7.4 times 10 to the negative 6 molar per minute. So what seemed very hard, it really all falls into place. The last question seems hard, but it really just relies on what we learned at the very beginning. It says calculate the initial rate of disappearance of mercury 2 chloride in experiment 1. Okay. If we look at the data table, we see in experiment 1, we're given an initial rate of formation for mercury 1 chloride. Okay, so what they're telling us then is that the change in concentration for mercury 1 chloride over the change in time is 1.8 times 10 to the negative 5 molar per minute. That's given. And what they want to know is the initial rate of disappearance. So they want to know this. How do we write a rate equation from the balanced chemical equation? If you go back to your balanced equation, you're looking at the first reactant and the last product. So what you've got there, reactants are -1 or +1? -1 over the coefficient, change in concentration over the change in time, and that's equal to +1 over 1, change in concentration over the change in time. We're looking for this piece. We have -1/2, I'm going to call this x, is equal to 1.8 times 10 to the negative 5 molar per minute. I'm then going to multiply both sides times -2, just like you learned in pre-algebra. And what you have then is you have -3.6 times 10 to the negative 5 molar per minute. Okay? So basically we're able to combine almost every concept we talked about with one big question. Also, most importantly, rate laws clearly illustrate the effect of increasing concentration on the rate. Now, if something has a negative order, no, you're not going to see that increase in concentration resulting in an increase in rate. If something has 0 order, you won't see it either. Generally speaking, an increase in concentration increases reaction rate. Okay. Also here, the next 2 problems are a little bit funky. I don't believe it's anything they will ask you anymore. I think it's a very interesting topic. I'm going to film it on my own for you so that you can see it. But it really is very cool when you can hold this constant, look at the effect of doubling this on the rate, but then you can't hold this one constant. And there's a trick you can do to figure out the rate law. I'm going to film myself separately on this question and this question. It's not something you'll be responsible for, but when you go to college, you might kind of like it. Or if you want to learn separately, you're welcome to come in one morning or at lunchtime, and I'm more than happy to show you. We're going to pick up with integrated rate laws next time. Those are going to be very, very different. For those of you in calculus, I think you'll like the derived versus integrated concept. We still have a few minutes before the bell rings. Most importantly, you want to be comfortable writing rate laws today. You want to be able to analyze your rate laws, and we'll do a little bit more of that. You want to know the difference between a rate law and a rate equation. That POGIL packet I gave you should already be done, but certainly for Monday. At the end of your chapter in your textbook, if you go on Edline and look at that syllabus tab, there is a course outline which many of you have already played with if you've been successful in the course so far. You want to do as many rate law problems as you can with ease. You should have mastery of rate laws by Monday. Next week we'll be going into integrated rate laws and reaction mechanisms. The kinetics unit is very simple, and it's a good way to start off the next quarter on the right foot. So make wise choices and really make sure you're comfortable with it.